Thank you very much. Yeah, thank you very much. And thanks to all of you for joining me on this journey south. We're traveling a few thousand kilometers south to essentially the bottom of Earth. So this is where you find the majestic Antarctic Ice Sheet. And it wasn't even that long ago that the great explorers and adventurers set out on the same journey to discover the last continent. One of them was Sir Ernest Shackleton. And, well, even though at this point in time the Antarctic Ice Sheet was widely still unknown territory, he still had some idea of what to expect on this journey. And you can see this from the job ad that he put out in order to recruit men to come with him. There it says, "Men wanted for hazardous journey, small wages, bitter cold, long months of complete darkness, constant danger, safe return doubtful. However, honor and recognition in case of success." I don't know how many of you would join him on this kind of journey and adventure. Well, sure enough, about 100 years later, almost exactly 100 years later actually, I set out on the same journey. I joined an expedition to Antarctica. And even though I cannot know for sure what Ernest Shackleton and his men saw when they first arrived there, I'm almost certain it was something like this. This is my very first impression of Antarctica when we arrived there, and I remember it like it was yesterday. So it was actually during the night, and I woke up, and you have to imagine this was in summer, so we actually had 24 hours of daylight. And I woke up all of a sudden because it had become pitch dark in our cabin. So I ran upstairs to the deck to see what was going on, and I still couldn't see very much. And then I looked up, and in front of me was really this steep wall of ice just reaching out of the ocean. And this was one of the first pictures taken in that moment. Yeah, as you can see, this is really like a cliff of ice, and at this particular spot, about 30 meters were reaching out of the ocean, so above sea level, which means that all in all, this wall of ice at this point was about 300 meters thick. And I was just utterly impressed by that sheer size of the ice shelf edge. And I also remember thinking, well, no wonder they call this the eternal ice, because, I mean, if something this massive, it really seems like nothing could ever change this or really affect this. Well, I was really wrong about that. So this was the expedition back then, and you really can be impressed by the sheer size of the Antarctic ice sheet. In fact, Antarctica is kind of the continent of superlatives. It is, of course, the coldest place on Earth, but also it is the windiest place on Earth. And what might be most surprising, it's also the driest continent. And this is, although almost the entire continent is covered by a really thick ice sheet. In some places, this ice sheet is more than 4,000 meters thick. And if you imagine this, this is like stacking a dozen Empire State Buildings on top of each other, all made out of ice. So the sheer size is impressive. And this is really a massive ice sheet. And the question is, yes, this is all really fascinating and interesting, but why should we care? Why should you care? And I think two numbers that really summarize this very well are these ones. This is the so-called sea level potential. And what this means is, if the ice sheet melted down and you took the meltwater and distributed it over the entire ocean, this is how much sea level would rise globally. That means that the Western Arctic ice sheet alone holds enough ice to raise global sea level by more than 5 meters, and East Antarctica the tenfold, so more than 50 meters worth of sea level rise are stored in that ice sheet. So this is naturally the largest freshwater reservoir on Earth, and it really deserves the label, the sea level giant. Now, of course, the ice sheet has been around much longer than humanity, and it has undergone some massive changes in the past. In fact, Antarctica is kind of a fantastic calendar of climate change because it records the CO2 content in the atmosphere and also the temperature And here you see data from ice cores dating back more than 800,000 years. As you can see, the ice sheet has undergone a number of glacial cycles, so alternating between cold glacial times and warmer interglacials. And today, we're at a very specific point in time. Today, we are at in interglacial time, but as you can see, anthropogenic climate change means that we have really crossed this 400 ppm parts per million line in the past. And parts per million, well, that sounds not very much, but as you all know, this change in the CO2 content means that the temperature of the atmosphere has risen by roughly 1 degree globally. So we really are at this specific point in time, and if we zoom in into those past 20,000 years, we can look at the temperature evolution a bit more closely. So this is the evolution since the last glacial maximum about 20,000 years ago up to today. And there are two really striking features about this curve. First of all, you will notice that in the past thousands of years, which is actually when humanity has mainly developed its civilizations and societies, and during that time, climate was very, very stable. And the other thing that you will notice is that the difference between the last glacial maximum about 20,000 years ago and today, this difference is roughly 3 to 4 degrees. And these 3 to 4 degrees, if we now look at some future scenarios, we can compare this with the warming levels that we might reach within this century or within the next centuries. And this is what's done here. You see 4 different potential temperature pathways for the future put out by the IPCC. And you see that we might face the same magnitude of warming, the difference between an ice age and today, but in a much, much shorter time scale. And we can all agree that there is a huge difference between a glacial time and ice age and today's climate. And so we can also assume that there will be a large change between today's climate and the future climate and dynamic changes in the Earth system through this temperature change. So keeping all of this in mind, it's quite natural to assume that maybe the eternal ice is not that eternal after all. And you might have seen some of these headlines in the recent past. And all of these show kind of the same thing, namely that the sleeping giant is actually much more active and much more dynamic than we might have thought. And here you see some headlines put out about ice shelves calving, about icebergs forming, about meltwater ponds on the surface of Antarctica, about glaciers speeding up, about glaciers thinning. And this is what I look at in my research, are these changes, these observed changes, and the processes behind them. So I try to understand the physics behind what we see, and also to see what we can expect for the future. So I travel to Antarctica every day, but through my computer. And what I look at is this type of code. This is our open source parallel ice sheet model, PISM. And I look at these equations, which are essentially based on what we all know from high school, and that is mass conservation, energy conservation, and momentum conservation. And based on these equations and the very complex dynamics of Antarctica, I try to understand better what is going on, why we see these changes in Antarctica, and what we might expect for the future. And one thing that's really interesting is that even if the ice sheet is in equilibrium, which is what you see here in sort of this artificial equilibrium simulation of Antarctica, even in equilibrium, the ice sheet is constantly moving. And that is because there is snow falling on top of the ice sheet, and that is compressed into ice, and then due to this gigantic weight of the ice, it's just pushed out towards the ocean. So you have a constant flow of ice towards the ocean, which is then being replaced by snowfall on top of the ice sheet. And of course, under global warming, the conditions of this change a lot, and the ice might speed up. And one of the reasons why Antarctica was in the news so much lately is this observation here from West Antarctica. So this is sort of a zoom into the so-called Amundsen Basin. And what you see here is, in this red color, is that the glaciers over the past decades have really sped up in this area. And not only have they sped up, they've also retreated to the back valleys here. And the reason why this is specifically alarming lies actually at the bottom of the ice sheet. So let's look at a cut through Western Antarctica. It looks something like this. So what you see here is, first of all, the ice sheet sitting on bedrock. And you also see a specific feature that's very common for Antarctica, and that is that towards the ocean, the ice forms so-called ice shelves, so floating extensions of the ice sheet that, of course, do not contribute to sea level rise directly. It's much like the ice cube in the water glass. But nonetheless, they play a very important role because they act kind of like plugs or buffers for the ice flow from the interior towards the ocean. And the separation line here between the inland ice sheet and the ice shelves, the floating extensions, that is what we call the grounding line. And the position of this grounding line is very important for the ice dynamics and also for sea level rise. And in West Antarctica and also large parts of East Antarctica, we have a very specific bottom topography, and there are two conditions that are important. One is, as you can see here, that large parts of the ice are actually grounded below sea level. And the second condition is that the land declines land inward. And whenever these two conditions hold, the ice is prone to an instability. So since it does hold in large parts of Antarctica and also in the Amundsen embayment, this is why these observations are so important. So again, here you see the zoom to the Amundsen embayment with the largest and also the fastest glaciers of Antarctica, Pine Island Glacier and Thwaites Glacier. And all of these glaciers in this region have accelerated, and they have now retreated into the valleys behind, and there's no hills or mountains that could somehow buffer the ice flow from the interior towards the ocean. So this region has likely become unstable, and this means that on the long term, we will see about 1 meter of sea level rise globally from this entire region. Now, we don't know yet how fast this might happen, and we also don't really know if this is directly linked to anthropogenic climate change. But with our ice sheet model, we can look at some of the consequences of this. And this is what was done here. You see a simulation with a parallel ice sheet model where essentially the Amundsen embayment, the purple area here, was destabilized. And it's important to note that there is no other forcing, so no warming, no change in snowfall, no change in melting. There's just this one meltwater pulse which destabilizes that region, much like we see in the observations. And the rest that you see is just the internal dynamics of the ice sheet. So if the meltwater pulse is long enough, then this happens. So you see here how just through the destabilization of the Amundsen embayment, in fact, all the marine parts of West Antarctica become unstable, and you have this long-term sea level rise of about 3 meters. There's something really important to note here, and that is sea level rise takes a very long time. And this is important to keep in mind because we are very concentrated on the next decades and the next century, but really for sea level rise, the time after that is just as important, and the bulk of sea level rise will actually not happen this century, but much after. So we need to think of sea level rise in terms of commitment. And you could ask the question, well, how far does our influence reach? How much do we really affect the Antarctic ice sheet? And this was actually a question. I'm sorry, I have a problem with the mic here. Hope this works. This question was already posed in the New York Times in 1979, so really a long time ago. And it is just as relevant, or even more relevant today. So we looked at this with our ice sheet model and looked at all the possible future states of Antarctica with several different greenhouse gas emission scenarios. And you will see that the fate of Antarctica really depends mostly on how much greenhouse gases we emit and have emitted and will emit in the future. And the future state of Antarctica can range from anything like essentially an almost intact ice sheet when we have no further greenhouse gas emissions to sort of an intermediate state for still rather moderate greenhouse gas emissions, where you lose, just like you saw in the animation before, parts of West Antarctica and also the Wilkes Basin here, for instance, in East Antarctica. And if we were to use up all the fossil fuels that are available to us, then Antarctica could become almost ice-free on the long term. Now, these are very long-term trajectories, but it is important to note that this entire range is possible, and it really depends very much on our greenhouse gas emissions, on our actions today. So in terms of, if we look at our coastlines, then what does this mean concretely? This is still a rather moderate emission scenario that stays within the 2-degree range that was agreed upon in Paris. And what you see here in purple are all the areas that might be submerged or below sea level in the future, where today more than 50 million people are living. So this means that on the long term, we really need to think about sea level in terms of commitment. And on the long term, even under moderate emission scenarios, in order to save our coastlines and protect them, we need to really reduce greenhouse gas emissions and actually reduce them down to zero in order to keep this cultural heritage and these cities from these effects. So bearing all of that in mind and coming back to this very first picture, you can really see that Antarctica can be unplugged, and that it's important to think about these long-term changes. We really have to keep in mind that sea level rise is nothing that happens in the next year or in the next decades, but our actions in the next years and in the next decades, that is what will change Antarctica and the face of the planet for centuries or millennia to come. So humans really have become a geological force, and it's very important to, even though it seems far away, to bear Antarctica and all these changes in mind. Thank you very much, and I look forward to questions. Are there any questions?
If you have any questions, we have a microphone here to record your question. I will take all of your questions, the good and the bad ones. Yes, there in front. I will come to you, wait.
Well, you mentioned that when you showed us the different pictures, how the emission could influence the Antarctica in the future, but you said it's only thought how the emissions would change, but is there any other way this could be reached? Like if we stop the emissions and from that point we see that Antarctica wouldn't change, but is there any possibility that there's anything other that could arise in the future that could change it to that? Or to this different state?
That's a really good question. So what's important to keep in mind that there's a lot of inertia in the system, and that means that changes today in the climate might affect Antarctica for a really long time because the ice flows so slowly and also adapts very slowly to these changes. So in principle, yes, there could be many different changes. For instance, also if sea level were to rise from, say, Greenland ice loss, that would have an effect on Antarctica, even though the two ice sheets are on opposite sides of the globe. So there are lots of changes in the climate system that can affect Antarctica. But overall, what's important to keep in mind is that the greenhouse gas emissions and the anthropogenic climate change coming from these greenhouse gas emissions, that's really what decides the future state of Antarctica.
Besides the sea level rise, the Antarctica, since it's sweet water, also affects the ocean's, I think, weather circulation, what we get, what kind of wind we get, or warm water currents, and what, like, do you have also how many meters sea level rise do that correspond to? How long will that take to feel the affections actually of changing weather just because we have more sweet water in the oceans?
So yes, a very good question. So this is actually true for both ice sheets. So for both Greenland and Antarctica, it's true that if large parts of them melt, then this leads to a freshwater inflow in either the North Atlantic or in the Southern Ocean. And due to this freshwater inflow, as you just said, the ocean circulation might change. And as you know, a big part of the ocean circulation is what is called the conveyor belt of the ocean circulation, so the thermohaline circulation. And this is, for instance, what brings our moderate, warm climate here to us in Europe. And that means that whenever we have large changes in Greenland or Antarctica, this might change as well. And it's really important to see how, even though these ice sheets are sitting at the poles and seem kind of far away, they have a direct effect on our climate here as well.
I have a question concerning the lives in the Antarctica. Do you also look into the microscopes, the penguins, all those wildlife over there, and what is the effect of this melting? Thank you.
Yeah, that's certainly very interesting. So this is not part of my everyday work, but of course it's a very important question. What kind of life do we find there? And I know that there are some really interesting publications out on that. For instance, on microbes that live underneath that really thick ice sheet that were found. But I'm not an expert on this, so this would be a question really for maybe a biologist or an ecologist somewhere about Antarctica.
Hello. What do you think about the loss that the subject climate change has at the moment in the medias? Like, I noticed that the topic was quite big a few years ago, but it loses constantly in place, like actually the ice.
That's also a really important question. So communication of these results, I personally think is really important. I'm not sure if it is true that there is less attention to this. I certainly hope that that is not true, because, like I said, one of the problems with ice sheets is that they do seem rather far away, and we kind of feel like we have, still a long time to go until we actually see changes from there. And I hope I could just convince you that that's actually not true. We are already observing changes in Antarctica and also in Greenland, actually. And these changes are just as important for us today.
And there's time for a last question.
Since you have worked there, also at the Antarctica, how is the relationship between other scientists from other countries? Do you have met them, and how is the working experience with other countries on that? On that continent?
Yeah, certainly a very good working experience. So I was there on a research vessel, and this expedition was led by the Alfred Wegener Institute. And there are many different research groups on one research vessel. They come from all over the world and work together also on very different topics. So on the ice sheet, but also on the ocean, on the sea ice. So all of that is really important. And we have, along the way, also visited some of the research stations from other nations.
Thank you very much.
Thank you very much.